All right, so today we're going to be going over the Unit 9 test review for gas laws and gas stoichiometry. This section is for numbers 1 through 6. On number 1, it says, under what condition does a real gas display the most ideal behavior? Okay, so ideal gases are ones that follow the kinetic molecular theory, which means that they don't take up any space, that they don't get attracted to one another or to their containers, that they move in constant random motion, and that those collisions that they do make are perfectly elastic, meaning that there's no energy loss to friction. So typically, real gases follow the ideal gas in a wide variety of temperature and pressures, but no gas is truly ideal. So under these conditions listed below, we've got to figure out which one would actually follow the ideal behavior versus which of these would actually make it not ideal. And real gases deviate, meaning they don't follow ideal gas behavior at high pressures and low temperatures. So let's see if we can find answer choices here that would indicate high pressures and low temperatures. So obviously C is wrong because it says when a gas is cooled. So we know that we don't want to cool the gas because that would be low temperatures. So we know it wouldn't be following the ideal gas behavior then. And when volume is low, that means that pressure is high. And we know that from Boyle's law. So we know that D is incorrect. And then when kinetic energy reaches zero, well, when kinetic energy reaches zero, the only place it can do that is at absolute zero for temperature. And we already said that we don't want really low temperatures. So that leaves us with the answer choice B, when gas molecules or particles are far apart. And this is true because when they're far apart, they're less likely to be attracted to each other, which would allow them to follow the kinetic molecular theory, which is that they're not attracted or repelled by each other or by their container. So if they're far apart, that makes it less likely for them to be pulled towards each other. Okay, number 2, what is the definition of pressure? Pressure is simply the force per unit surface area. What does this mean? Okay, so the easiest way I can describe this is if you hold out your hand and then you put your palm on top of your other palm and push down, okay? All right, now remember what force or how hard you're pushing with. And then instead of using your palm to push on your other palm, take just a finger and push into the center of your palm with the same force. And you will feel more pressure in the center of your palm. It will hurt more. And the reason why is because you're putting the same amount of force in a smaller area, just the tip of your finger is touching your palm versus your entire hand touching your palm. So that's the concept of pressure. All right, atmospheric pressure is measured with a barometer. We talked about this before when we talked about weather. Okay, and we talked about the hurricanes and everything. All right, number 4, a pressure of 350 millimeters of mercury, Hg is mercury, equals. Okay, so this is just an equivalent statement. All you're trying to figure out is your relationships between your different pressure measurements, your different units of pressure. So in our answer choices, we have ATM, which is atmospheres, we have kilopascals, we have pascals, and we have torr. All right, if you look at your formula chart, under the constants and conversions section of your formula chart, you'll see, I don't know, I guess 3/4 of the way down, it'll say 1 ATM or 1 atmosphere, is equal to 760 millimeters of mercury, and that is equal to 101.3 kilopascals. Okay, so now 350 millimeters of mercury. Okay, we know that 760 millimeters of mercury is equal to 1 atmosphere, so we know that 350 millimeters of mercury can't equal 350 atmospheres, because 760 equals 1, so they can't be equivalent to each other. They would have to have the same relationship. It'd have to say over here, in this section here, it'd have to say 760 atmospheres equals 760 millimeters of mercury for them to be the same. And so this is also true for the kilopascals as well. 101.3 kilopascals is equal to 760 millimeters of mercury. So we know that that the kilopascals and the millimeters of mercury can't be equivalent. Well, kilo means 1,000 pascals. Okay, so that means that we can say that this is equal to 101. Okay, so remember it's 1,000, so now we just move it over 3 places. 3, 0, 0. Okay, so all I did was move that decimal over 3 places, and that is pascals. Okay, so now, again, if we look at this equivalent statement, 760 millimeters of mercury is equal to 101,300 pascals. Again, these two numbers are not equivalent to each other, so we know that it can't be 350 pascals. All right, so even though we don't have torr on our formula chart, it's the only answer choice left. And as a matter of fact, 1 millimeter of mercury is equal to 1 torr. So they are exactly equivalent to each other. So the answer choice is D. But you can do this straight from your formula chart with some common sense, understanding that atmospheres, millimeters of mercury, and kilopascals are not equivalent to one another. So the numbers here, this 350, 350, 350, 350, cannot be the same. And if you understand that kilo means 1,000, you can also figure out what your pascals number is by just moving your decimal place over 3 places, multiplying by 1,000, in other words, to get it to pascals. And again, it's not equivalent. So that leaves us with torr just by process of elimination. All right, number 5. Number 5 says, which of the gas laws is calculated when pressure and volume variables at a constant temperature? All right, so we're keeping temperature constant, and we're changing pressure and volume. All right, well, the only law that deals with pressure and volume changing is Boyle's. All right. Number 6 says, blank was a Frenchman whose interest in hot air balloons led to an expression relating volume and temperature. Okay, so the only equation that relates volume and temperature is Charles' law. So Charles was the Frenchman that came up with this, and remember the relationship, the equation is that your volume and your temperature are related, and they're directly related. So as the volume increases, the temperature increases, or you can say as the temperature decreases, the volume decreases. You can say it any way you want to. They're directly proportional to one another. And remember, the equation for that is your initial volume, V1, over your initial temperature is equal to your final volume over your final temperature. So there's the equation for Charles' law.